Hey everyone, welcome to the Algebra 2 Semester 1 review, which is mainly just Module 2 Topic 3 about rational functions, but it covers the review packet that you can use as notes on the final, which is partially cumulative, like it's got stuff from the whole year, okay? I said to my class I would have this posted by 5. It's currently 3:54. By my calculations, that leaves me not enough time, so I got to get going, okay? Here we go. So first problem. We did this one in class. If you already watched it, you can skip it, but whatever. Anyway, here we go. We're going to graph this rational function, and we're going to do that by finding the vertical and the horizontal asymptotes and then plotting some points around them, okay? So the vertical asymptote happens when we divide by 0. When we divide by 0. It's a value of x that makes there no possible output there because, no possible input. It's a value of x that makes me divide by 0, which is illegal, right? That means you're going to get locked up by the math police. And let me tell you, the industrial mathematical prison complex is not one you want to be a part of, okay? So we have to be careful when we divide by 0. We can look, but we can't touch, all right? So here we go. -4 over x plus 3. I'm trying to figure out what value of x makes me divide by 0. Well, it's just whatever makes the denominator 0, which is just x equals -3, right? If I plug in -3 here, plus 3, I get 0. All right, so I know my vertical asymptote is going to be at -3. So I'm going to draw an up and down dotted line right there, okay? It's like a barrier. It's like the glass. All right, now, horizontal asymptote, in order to find this one, we have to look at a couple of things. We have to look at the degree of the numerator and degree of denominator, okay? Now this one, if you have the translation notes or the transformation formation of rational functions, those notes, you can use that as to graph this, but I'm going to do it the long way. That works every time, okay? So the degree of the numerator divided by the degree of the denominator, that's what we're trying to figure out here, all right? What do I mean by that? Well, the degree, we're going to talk about this later, is the number of times you're multiplying x, right? It's the highest exponent above a variable. It changes things from like linear to quadratic. And so in the numerator, I don't even have an x, which means that this is degree 0. There's no x's to even look at. On the bottom, there's an x. It's x to the first power, which means that this is degree 1, all right? And then from our notes, we had this little table that I set up, but when the degree of the numerator is less than the degree of the denominator, that means your horizontal asymptote is at y equals 0. So horizontal asymptote at y equals 0, okay? So you might want to go ahead and plot a line at y equals 0, but hold on, because there's something funky going on in this equation, okay? There's something that's not in the next one, at least, down here, and it's this -1. It's this thing just hanging out on the outside. And this -1 is doing what a -1 does in so many equations, which is it's taking all the values and it's just subtracting them by 1, which means visually on the graph, this thing is going to translate everything down 1. Which means if my horizontal asymptote should be at y equals 0 for these normal equations, if I translate it down 1, that means it's just going to be at y equals -1. And so that's my horizontal asymptote here. Y equals -1. It should be at 0 based on the degrees, but I translated it down 1, okay? So once we have those two things, once we have the vertical asymptotes and the horizontal asymptotes, all I need to know is what's going on the left side of the asymptote, the vertical, and the right side of the vertical asymptote. And so I'm going to use some test points, okay? I'm going to pick some number that's to the left of a vertical asymptote and to the right of a vertical asymptote. Okay, I just need to pick two numbers in this case that satisfy that, all right? And so I'm going to pick x equals -4 because it's the closest number to -3, that's whole. And then I'm also going to pick x equals 0 because if I can test x equals 0, I'm always going to test it. Plus, we have to find the y-intercept anyway, which happens when x is 0. So what I mean by test points is I'm just going to plug these in, see what the output is, and I know that my graph is going to be on that side of my horizontal asymptote, okay? Really, I'm looking if it's positive or negative, or in this case, above or below -1. So let's plug in -4 into my function. I'm going to get this. I get g of negative 4 is negative 4 over negative 4 plus 3 minus 1. Well, that becomes negative 4 over negative 1 minus 1. So I said plus 1, sorry. That is positive 4, because a negative divided by negative is a positive. So 4 minus 1, which is 3. So when x is negative 4, y is 3, which is above my horizontal asymptote, which means my line is going to look something like this. Okay, something like that. Now, if you know the properties of rationals, you kind of know it's going to go on the other side, but we have to find the y-intercept anyway, so let's plug in x equals 0. That becomes this. Negative 4 over 3 minus 1. That's negative 7 over 3, which is negative 2.333 repeating, of course. And that is, I don't know, right about here. And that's also the y-intercept. When x is 0, y is negative 2.33. And that means our graph is going to look something like this, because it's always got to get super close to these asymptotes, but never quite touch them. That's what rational functions do, at least. So nice job. We've graphed it, but now we need to talk about the domain and the range. All right? We've done this a lot this year, and you're going to continue to do this forever until you take your last math class. But domain is just all possible x values. It's where your graph goes left to right, and then range is all possible y values. I'm not even going to write that out. I don't want to waste my time. Okay? So if I'm looking at where does my graph go left to right, really what I'm doing is if I just draw if I pick an x value and I move it left to right, where do I cross, in this case, my green line? All right? And so since I continue on forever to the left, I can go all the way to negative infinity. And so I'm going to say my lowest point is negative infinity. And I'm going to use interval notation for this. Whoa. And then if I'm scanning to the right, I can go all the way until I get very, very close to dividing by 0, and I'm not going to actually do it, so I get stopped at negative 3. And so I can go from negative infinity to negative 3. All right? And we're using the parentheses because we can't be equal to them. But then if I look, that's not the only green part of my graph. I also have everything over here, which happens from negative 3 to now positive infinity in the x. And so I need to include that in my domain, and the way we do that is by throwing in the union symbol, which is like a big U. And then I'm going to say that's negative 3 to positive infinity. All right? And there's a domain. I just scan from left to right. I'm going to get stopped by my vertical asymptotes. All right, well, what about the range? The range is the same thing, but instead of left to right, we're going bottom to top. And so when I look here, this line goes down. Oh my gosh. This line goes down forever, which means I can go all the way from negative infinity until I reach my horizontal asymptote, which is right here at negative 1. And that's where I get stopped. But that's not the only place I can go, because I can actually go above it. I just can't be at negative 1. And so I have to throw another union in, and then that's negative 1 to positive infinity. Okay. Oh, gosh. And that's in terms of the y. All right. So that's how you graph a rational function that looks like this. I just need to lock this. Let me just lock this real quick. Let me just lock this. Lock in place. Now I can't move it around. Nice. Okay. So that's how you graph one that looks like this in transformation form. But, my whole thing shifted around. Hold on. There we go. But what if it's in this type of form with a bunch of stuff that we have to factor? Well, guess what? We got to factor it. And you're going to have to factor like 10 times on this test, because that's all Algebra 2 is in general. This problem actually gives you a little hint, though. The numerator could be factored by difference of squares, because I have two squares. And difference of squares means I can take x plus 5 times x minus 5 in this case. It's the two things that multiply to negative 25. These two things multiply to x squared, the x and the x. But if I look in the middle, I would end up with 5x and negative 5x if I multiplied this out, which would cancel. So that's why this works, this shortcut. The bottom one, we do have to factor using our normal method. We're trying to find two numbers that multiply to 20, add to negative 9. That's going to be negative 5 and negative 4. Okay, so that's what that's going to turn into, is that's going to make our function x minus 5 times x minus 4. All right? However, if we can simplify these rational functions, we should, because it's going to make our life graphing them so much easier. And in fact, it's going to be an accurate version of this graph. And because I have something on the top, this x minus 5, that's also on the bottom, anytime anything I divide by itself, I just get 1. So I'm going to cancel these out. And I'm going to rewrite my new one, my simplified version, as x plus 5 over x minus 4. Like that. Okay, in fact, I don't even need the parentheses anymore. Oops, we can come back. Now, you can't just cancel things in the denominator, especially if it's x, with no repercussions. We got to be careful because, like I said, dividing by 0 is a serious issue, all right? And it's taken very seriously in the world of math. And if I just cancel things with no regards of the potential of dividing by 0, well, then I haven't done my due diligence. And what I mean is, when I cancel this, I have to be careful because there is a value of x in my original function, which is the thing that I really care about. There's a value of x that if I plug it in, it's going to make me divide by 0. And that is positive 5, right? But I just canceled it. If I plugged in positive 5 into my simplified version, nothing would happen. But when I plug it into my original version, I'm taking 0 divided by 0. And anytime that happens, that's when there is a hole. And so that means at x equals 5, there is a hole in my function. That means it's a domain restriction, okay? Then after we do our simplification, after we care about our holes, we are now going to find our vertical asymptotes just by figuring out what makes us divide by 0, which in this case is x equals positive 4, because that's what makes my denominator 0. And so I'm going to draw an up and down line at x equals 4. I don't know where my graph is. I'm just doing it there. All right. Now, before we graph anything else, I want to do the horizontal asymptote. I know it says bonus, but in my eyes, I want to graph it. That way I know what my graph looks like. Okay. So this is the second case. In the first case, the numerator was less than the denominator, the degree. In this case, since they both have just regular x's, x to the first power, the degree are equal. Okay? When that's the case, when the degrees are equal, to find the horizontal asymptote, you divide the leading coefficients. The leading coefficients. Those are just the numbers that are in front of x, which in this case, what numbers are in front of x? Well, nothing, which means it's really just the number 1. It's the invisible multiplier. And so we would just take 1 divided by 1, which is 1, which means the horizontal asymptote is at y equals 1. And so I'm going to draw a line at y equals 1. Nice. Okay. So once we have those two things plotted, we're going to do the same thing and test some points. Okay. Test points. Test points. Test points. It's a verb and it's a noun. Okay. So I want to pick something to the right and to the left of each vertical asymptote. I see that x equals 0 is to the left of my vertical asymptote, right? And so I'm going to plug that in. I also see, x equals 5 is to the right of my vertical asymptote. And so I'm going to plug that in. I'm going to see what's going on around those points, if they're above or below my horizontal asymptote, and then I'm going to plot it. All right, so here we go. When I plug in x equals 0, I can use the simplified version now. And so I'm going to just plug in x equals 0, and I get 5 divided by negative 4, which is negative 1.25. That's also my y-intercept, which is very nice. Double dipped. So that means I have a point at when x is 0, y is negative 1.25 or something like that. Okay. Then I need to plug in a point to the right of my vertical asymptote. We said x equals 5, and that becomes this. 5 plus 5 over negative 4. 5 minus 4. That is 5 plus 5, which is 10, over 1, which is 10. So when x is 5, the output is 10, which is like up here. Okay? So that means that my graph is going to look something like this. Wait a second. What did I just do? I just plugged in x equals 5. Wait, hold on. There was a hole there. Whoa, no, what did I mess up? Did I do something wrong? Well, no, not really. That would be the output if I could legally cross these out. But because I divided by 0, technically there's a hole there. And so I'm going to actually just put an open circle at x equals 10, and then, or sorry, y equals 10, and then draw my graph around it. So I know that my line is going to go infinitely close to this vertical asymptote. It's got to swoop through my y-intercept, hit somewhere across the x-axis, which we'll find in a second, and then go infinitely close to this horizontal asymptote. That looks so bad, I'm not going to lie. All right, let me try again. That's not better. Okay, let me try it. Let me try one more time. My hand was covering it, and I could not see what I was drawing. Okay, here we go. Ready? Much better, much better. Okay. And then, because I have this hole up here, I know that all of it's going to be up above the horizontal asymptote. It's going to look something like this. All right. So this would be the output, but it's actually a hole. All right. And then last but not least, they tell us to find the x-intercepts. Well, on my graph, I can see I only have one. And so let's figure out what it is. Okay. Well, if I want to know the x-intercept, I just want to know when y is 0, which just means what happens when the numerator of the fraction is 0. And so I'm just trying to figure out what makes this equal to 0, which is x equals -5, or the point -5, 0. And that is my x-intercept. It's just the value of x that makes the numerator equal to 0. Okay? So cool. We've done 2. They're both pretty complicated. You might have a different way of doing it based on the transformation form and whatnot, but I like doing the test points way. Always just graph the asymptotes and then see what goes on around it. All right? No shortcuts in this house. All right. Here we are on other rational expressions. This one is all about how do we operate with them? How do we take two fractions with a bunch of x's in them and multiply, divide, add, and subtract? Okay. And so here's what we're going to do. In a lot of these problems, we're going to have to factor. And so if you're not brushed up on your factoring skills, well, now's the time to do it. This problem actually tells us the different methods we can use, but I'm just going to use my brain to do it, all right? So up top, x squared minus 9, that's going to factor into x plus 3 times x minus 3, because it's a difference of squares, right? Which it actually says right here. So you figure out, how do I get to -9? Well, I got to multiply 3 times 3. How do I get to x squared? I got to multiply x times x, okay? And then for the bottom, I'm going to have to use this. I'm going to say -21 up top, 4 on the bottom. I need two numbers that multiply to -21, add to 4, okay? And I'm going to use the shortcut because I just said no shortcuts. Sometimes shortcuts in this house. All right, there's no number in front of x. It's just 1x, so I don't need to use the box method. But you can if you want. And in fact, you will later in the problem. So, don't get too happy yet. And so I need to find two numbers that multiply to -21, add to 4. That's going to be -7 and 3, which means the bottom is going to turn to x minus 7 times x plus 3. And we are multiplying by x plus 4. Oh, sorry, I did that wrong. It's +7, -3. Because I want +4 that they add to. So let me rewrite that. Sorry. X plus 7, x minus 3. And we are multiplying that to x plus 7 over 3 times x plus 3. Oh, gosh. 3x plus 3. All right. And so after we've done this factoring, let's see if anything cancels. All right. Well, right away, I see that this x minus 3 cancels with this one. All right. So get rid of it. That becomes x plus 3 over x plus 7 times x plus 7 over 3x plus 3. And when I multiply fractions, all I have to do is multiply top to top, bottom to bottom, which means this really just becomes this big fraction. X plus 3 times x plus 7 over x plus 7 times 3x plus 3. Okay? Well, already I can see something else that cancels. It's this and this, which means this is x plus 3 over 3x plus 3. But wait, the very last thing that they say is the second fraction using the GCF. Well, because there's actually a hidden thing that's going on in here. Actually, no, I think that's it. in the denominator of the second fraction using the GCF. Is there something that's going on here? I can factor out a 3 from this. I can take this as x plus 3 over 3 times x plus 1. But I think that's it. Maybe I did something wrong. I don't know. I don't have time to restart. Okay, I think that's the answer. I think this should be 9 if they wanted them to cancel. But either way, it's cool. All right. Factor the denominator. Oh, the second is using GTF. Sure, I guess you can write it like this if you want. Either one works for me. All right, so let's keep going. Now we're going to divide two fractions. And so let's just factor again, rewrite it, and then we'll do the division. Okay, so I need to keep everything the same except for this first denominator because I'm going to factor it. So I need two numbers that multiply to 16, add to -8. That's going to be -4 and -4. So that becomes x minus 4 times x minus 4. Okay. All right. Now, when you want to divide two fractions, you can actually use a little short. Well, it's not a shortcut. It's just the method to know. Dividing is the opposite of multiplying, right? And so if we're dividing a fraction, which fractions are just dividing, then we're doing the opposite of dividing, which means that we're multiplying by the reciprocal of a fraction, right? Dividing is the same as multiplying by the reciprocal. This is the rhyme that Zeke's taught me. Dividing fractions is easy as pie. Flip the second and multiply. So let's do it. I'm going to keep the first one the same. Keep the first one the same. Flip the second one. Make it x minus 4 over x plus 1. And now change the sign from division to multiply. I like to say skip the first one. Skip it. Flip it. And then ship it. Ship it means multiply. So let's do it. This becomes x plus 1 times x minus 4 over x minus 4 times x minus 4 times x plus 1. That means that this is going to cancel with this. This is going to cancel with this. And all I'm left with on the top is kind of nothing, which really means it's just 1 over x minus 4. And that's my final answer. Cool. So the dividing and multiplying ones, they're longer process, but they're kind of easier in a way. I don't know. Because adding and subtracting fractions, in my opinion, is much harder. But here's how you do it. In order to add and subtract fractions, we need to have a common denominator. We need to have a common denom. Okay? Com denom, as they say. Just like we were adding normal fractions, we can't add 3/7 plus 1/2. We got to change this around to have a common denominator. And so what that means is I need to figure out a way to multiply these fractions by something over something. It's going to be the same thing because that's the only thing I can really do to keep it okay is to multiply by 1, which is just the same number over itself. That would get us to have the same thing on the top and the bottom of the fraction. And so here's how I'm going to do that. The closest way, or the fastest way to find a common denominator for these things with x's is to know that if I could just take x minus 6 and multiply it times 2x, that means I'm just going to get a thing that both of these denominators can go into, a common multiple, right? And so what I'm going to do is I'm going to take the first fraction and I'm going to multiply it by the second denominator over itself. So I'm going to take the first fraction and multiply everything by 2x. And I'm going to do the kind of the inverse of that in the next one. I'm going to take the second fraction and multiply it by the first denominator over itself. Now, all I'm really doing is multiplying by 1, right? I'm just multiplying by 1 because it's just the same thing over itself. So it's not changing any of the numbers. It's just making us have a common denominator. We're just like changing a fraction from 1/2 to 3/6, all right? And so let's do this math. Let's do this distribution. I got to multiply 2x times 5x plus 2. That's going to be 2x times 5x is 10x squared. And then 2x times 2 is plus 4x. And then divided by, same thing on the bottom. I got to do this. I'm going to get 2x times x is 2x squared. And then minus 12x. All right. Then on the second side, I got to do the same thing. I got to multiply 3 into that, or kind of that into 3. That means that on the top, I'm going to get 3x minus 18. And on the bottom, well, we're going to have actually the same thing because we're multiplying the same thing. So 2x squared minus 12. And now we have these functions that are these two rational expressions that we can add together because they have a common denominator. And so here's what it's going to look like. All you have to do is just add the terms on the top. You don't have to add the terms on the bottom. And so it's going to become 10x squared plus 4x plus 3x minus 18 over 2x squared minus 12x. And now we can combine like terms. I see that in the middle, I have 7x here. And so this is going to become 10x squared plus 7x minus 18 over 2x squared minus 12x. Sheesh Louish, man. Sheesh Louish. Now, you could actually go above and beyond. You could factor this. You could find a common denominator, or find something in common, a common factor, and pull that out. And that's my challenge to you, is to factor this. I actually don't know if it's factorable. Two numbers that multiply to negative 180 and add to 7, no idea. Don't know if it works. Doesn't matter. I'm going to leave this as my final answer. Okay. We've put it all together. We've smushed it into one fraction. That's good enough for me. But if you really want to go above and beyond, factor it. Okay. Maybe you can. Or maybe I did something wrong and it completely cancels out. And if you see that, yell at the video and write a comment. Okay. But I don't have time to restart. Here we go. Next one, we're going to subtract two functions. We still need a common denominator, which means I'm going to do the same process. I'm going to take these two things, and I'm going to multiply them by the opposite denominator. I'm going to go x plus 1 times x plus 3. So I multiply x plus 3 on the top and bottom of the first thing, and then I'm going to multiply x plus 1 over x plus 1 to the second thing. That's just going to give me a common denominator. Let's see what happens. I'm going to do this times this. That's going to give me x squared plus 3x, and then I'm going to subtract 5x plus 5. That's what happens when I do this times this, okay? And that's going to be over x plus 3 times x plus 1, and x plus 3 times x plus 1. I'm going to leave it like that just in case something weird happens. We'll see, though, all right? So now, when I subtract these two fractions, all I need to do is subtract the tops from the tops, leave the denominators, right? Because we're just finding a common denominator to subtract. But this time I want to be careful that I don't lose a subtraction along the way. And so here's what I'm going to do. I'm going to rewrite all of this, kind of like I did in this left one on the left, but I'm going to make sure I put parentheses around the thing I'm subtracting. And so I'm going to go x squared plus 3x minus all of 5x plus 5, okay? And then I'm going to divide by x plus 3 over x plus 1, all right? The reason I did the parentheses is because I have to subtract 5x and I have to subtract 5, meaning I kind of have to distribute this minus sign in. And so this is going to, in total, become x squared plus 3x minus 5x minus 5 over x plus 3 times x plus 1. That is going to simplify. Finally, I'm running out of room. I took too many steps. You guys can skip a step if you want. X squared minus 2x minus 5 over x plus 3 times x plus 1, which you could multiply out the bottom if you wanted to. Could we factor the top? Does it factor? Two numbers that multiply to negative 5 add to negative 2. That's only negative 5 and 1, which is not. So it doesn't factor. And so we could FOIL out the bottom. Or you could leave it like this. I'll write it as FOILed out just so it looks nice. It's going to be x squared minus 2x minus 5 over x squared plus 4x plus 3. And there's my final answer. All right. That concludes everything that's new. All right. That concludes everything that's new, the Module 2 Topic 3 stuff. And now we're going to go back in time. We're going to do synthetic division once. We're going to do some graphing, and then we're going to do some quadratic forms, okay? So here we go. Let's synthetically divide. You could also use long division if you want, but let's synthetically divide, all right? So here's this process again. First things first, we need to figure out what are we going to divide by. That's x plus 8. And so that becomes the thing that's kind of on the outside of the synthetic division setup, except we know that this is the root or the r value. And so that's the value of x that makes this thing equal to 0, the x plus 8. And so really what I'm going to put on the outside is negative 8 here, all right? Then what goes on the inside of my synthetic division, all these coefficients, all these numbers. Now we got to be careful that we don't skip any powers of x, but we don't here. We have x cubed, x squared, x, and then no x. And so I'm just going to write their coefficients 2, 11, negative 4, and positive 3, okay? Now here's this process. First things first, we're going to drop this 2 down and put it right here, okay? Then I'm going to multiply negative 8 from my root times 2, okay? And that's going to go underneath the 11. So negative 8 times 2 is negative 16, and that goes here, all right? Let me make this red just to amp it up a little bit, okay? Then you're going to add these two and write it here. So 11 times negative 16 is negative 5, all right? Then we're going to do the same thing. Negative 8 times negative 5, that's going to be positive 40. And then we're going to add. So then we're going to add negative 4 plus 40 is 36. Okay? Then we're going to do negative 8 times 36. Did I do something wrong? Like, why am I doing? Why does this feel so weird? Why does it feel like the numbers are giant? What did I do wrong? Negative 8 times 2? I feel like I'm right. I don't know. What's 8 times 36, dude? What? 8 times 36? 8 times 36? Negative 8 times 36? Negative 288? What? 88. And then we add those together and we get negative 285 as my remainder. I'm going to say that that's not a factor because my remainder is not 0. The only way that it could be a factor is if the remainder is 0, but it's not here, right? It is certainly not, unless I did something wrong. In which case, did I do something wrong? I don't think I did. You tell me. Leave me a comment. Maybe I'm just fooling you, but I don't have time to restart. So here we go. I think I'm right though. You know what? Let me Google this. I don't have time to restart, but I do have time to Google it. All right. Which, you're like, it's like, how are you allowed to Google the answer? I'm not. I'm breaking the rules right now. Okay. What am I Googling? Oh, I'm gonna go, what's the way to do this? I don't know. Synthetic division calculator? Synthetic division calculator. Does it exist? Symbolab? All right, let's do Symbolab. Synthetic division. I want 2x cubed plus 11x squared minus 4x plus 3. I'm gonna take this number and I'm gonna divide it by x plus 8 and hit go. No, I was right. Yeah, I'm right. Okay. Yeah, this is totally. Yep. This is the negative 285 is the remainder. So yeah, it's not. It is not a factor. Nice, we did it. Sorry, my alarm bells were ringing that the question was weird, but it's just me that's weird. Okay. It was me that was weird all along. All right, next one. Here we go. The following problems are not required to be done to cover a complete review. I guess that's true. I don't know. You can do them if you want. But this is all old stuff. This is like old stuff. This is like module 1 stuff. This is graphing. Well, actually, this one kind of isn't. This is a little bit of combination. All right. So we're going to factor by grouping, and then we're going to use difference of squares, and then we're going to graph the function. All right. Well, what does factor by grouping mean? Factor by grouping means we have two groups, a group here and a group here. I want to find what's in common between the first two things and the second two things. All right, I'm going to pull out that biggest thing, the biggest thing that's in common between both of them. So what do I see that's in both of my blue section here? Well, there's an x, and in fact, there's an x squared. And so I'm going to factor that out. I'm going to rewrite this as x squared times what would be left over if I divide that out. What do I need to multiply x squared back into to get back to 4x plus 3? Well, I need to multiply it times 4x minus 5. All right? That's my first group kind of factored. I've grouped it. All right? Now, the second thing, what's in common between negative 4x and positive 5? Well, kind of nothing, which means the only thing that's in common between them is 1. But because I noticed that inside my parentheses here, my 4x is positive, I'm going to factor out something that makes the 4x positive. Meaning, right now it's negative, I'm going to factor out negative 1. And that leaves me with 4x minus 5 on the inside. All right? So I found two greatest common factors. And the way that you know that you've done it right is if you look, in parentheses, you have the same thing, right? They're both 4x minus 5. And the reason why this works is because we have two numbers. We have two terms. We have an x squared and a minus 1, x squared minus 1, that is multiplying 4x minus 5. See that? We have x squared minus 1, x squared minus 1, multiplying 4x minus 5. All right? So nice, we've done it. We've kind of factored it. However, there's still one more thing we can do, difference of squares, and that's hidden right here, this x squared minus 1. It doesn't look like it, but it actually is a difference of squares because x squared is a square and 1 is a square. It's just 1 times 1. And so this thing factors into x plus 1 times x minus 1, and then that's still multiplying this 4x minus 5. And that is my factored version of the thing that I'm going to go to graph. Okay, so I'm going to write that up here. X plus 1 times x minus 1 times 4x minus 5. All right? So now we're going back. This is like to October, okay? We're talking about degree, number of possible real roots, y-intercept multiplicities. I mean, this hopefully should ring a bell as soon as we talk about it. But the degree, remember, this is what we talked about at the beginning as well, is the greatest exponent above a variable. And in this case, if I look at my standard form, that is 3, right? The other way to figure that out is if it's in factored form, you count up all of the times that you're multiplying x, or really you're just adding the powers above the parentheses, which are all 1, which means my degree is 1 plus 1 plus 1, which is 3. And so it matches up, right? We know we did it right. My degree is 3, which means the possible number of real roots is also 3. Oops. Those are always equal, all right? So to find the y-intercept, all we need to know is when x is 0, what is y? So I'm going to plug in x equals 0 into this function, calculate it, that's my y-intercept, all right? So rewrite it, but get rid of the x's. That's going to be 1 times negative 1 times 4, nope, no 4, times negative 5. Well, this is just 1 times negative 1 is negative 1, times negative 5 is positive 5. So my y-intercept is at 0, comma, positive 5, because this thing turns into 5. Plot it. That's 0, comma 5 right here. Okay? Zeros in their multiplicities. These are the x-intercepts. These are the values of x that make my function have an output of 0. And the way that we figure these out is by looking at our sets of parentheses. We are going to figure out the values of x that turn these things into 0, these parentheses, because they're all multiplying each other. And so if I multiply anything by 0, it's going to turn to 0. So the first time that happens is when x is negative 1, right? That's going to be right here at 0, comma, negative 1, comma 0. The multiplicity is the number in the exponent, which in this case is just 1, or there's no number there, which means it's just 1. It's the ninja number. So as a multiplicity 1, what that tells us is what does the graph do at that point? It could either cross through the axis or it could bounce on it, all right? It could bounce over it. That's determined by the parity of the multiplicity. That's a fancy way of saying is it odd or even? If it is odd, then it crosses. If it's even, then it bounces. Okay? Since our multiplicity is 1, 1 is an odd number, and so it crosses. So I'm going to put a little C here just to remind myself. Okay? Let's do the same process for the next two. This one happens when x is positive 1. That's right here, 1, 0. That also has a multiplicity 1, which means it crosses. So I'll put a little C right here. Last but not least, we have to figure out when is this equal to 0. Well, we can do that kind of just by solving it with algebra. I'll go down here to do it. 4x minus 5 equals 0. Let's add 5 to both sides. I get 4x equals 5, and then I need to divide by 4. Then I get x equals 5 over 4, which is 1.25. X equals 1.25, also multiplicity 1. These are little arrows that I'm drawing. I don't know why I draw the arrows. You could just, I don't know, do that. That kind of looks nice. But I'm ruining everything. All right, multiplicity 1, which means it crosses. Again, that's a point, I don't know, it's right here. 1.25, comma 0, C. Right, so now I need to draw a graph that goes through all these points. And so let's think about it. We have two different options. We can either start down low or up high, all right? If I start up high and I take my function and I bring it down and I cross through my first one, we're trapped. I need to cross through my y-intercept up here, but I can't because I can't go back up through the axis. It's only these 3 roots. So that means I have to start down low because I have to cross up here, go through my y-intercept, cross through this x-intercept, back up here, and then end facing upwards. And there's my function. It looks exactly like that or something like it. I don't know. And then let's talk about the end behavior. So the end behavior is saying when x goes to negative infinity, that just means when you look at the left side of the graph, which way is your function, your graph, pointing? Which way is the arrow pointing? That means as I go to the left, which way is this arrow pointing? It's pointing down towards negative infinity, right? And then same thing, as I go to the right, which way is this arrow pointing? As x goes to the right, it is pointing up, which is to positive infinity. And there's your end behavior. Okay. You can also use the end behavior table from something. All right. Here we go, transformation time. Transformations are ways that we can change functions and how they look on a graph, and the ways that we can do that is by looking at the things that are different from our original function, all right? So our original function is x cubed. So I'm gonna just highlight everything that's not x cubed, all right? That means we have this 1/2 in front, that's gonna do something. We have this -4 inside parentheses, that's going to do something. The other parenthesis is just x being cubed, so that's chill, that's already there. And then I have this +1. That +1 is going to do something. And so in total, I count 4 transformations. 3 transformations. I can't count to 3. Sometimes it'll be 4, and it's if there's a minus sign in front of the first thing, all right? So let's talk about them. What does this number in front do? What does this 1/2 do? That changes the shape of the graph visually as far as stretching it or compressing it. The word that we use is dilate. Kind of like your eyeballs get dilated. Dilate by a factor of 1/2. I'm running out of RAM. That's why my handwriting's so bad. So we're going to dilate by a factor of 1/2. We've checked off this one. Check. All right. This -4, it's on the inside of the parentheses. What is that going to do? -4, what is that going to do? Well, that's going to change the input value, the x value. In other words, it's kind of going to change the value of x that I have to plug in for the function to have an output of 0, right? It's now kind of changing this point that it used to be just x equals 0. And so what this is doing is horizontally translating. It's going to move my graph left and right? It's changing x. Oh my gosh, my computer is not working. No, I can't write. Horizontally translate. I got to write really slowly. Oh, it's still not working. Translate. Okay. Now, the weird part about this one is when I subtract from x, that actually moves me to the right. And when I add to x, that actually moves me to the left. And so since this is subtracting, you got to think kind of opposite. This means we're going to go right 4. Translate right 4. Let me say translate. Don't just say right 4. Say translate right 4. Oh my gosh. That's an N. There we go. Horizontally translate. That's going to move me left or right. Last but not least, we have this +1. This thing shifts me up or down, kind of like in the very first problem. This one's going to move me up 1. So I'm going to say translate. Oh gosh, I'm trying so hard to not let it overheat. Translate up. Translate up 1. All right. And those are the 3 transformations. This one comes from the 1/2 at the beginning. This one comes from the 4 inside the parentheses, the -4. And this one comes from the +1 at the end. All right. I believe we have one more problem. If we don't, I might just call it. It's pretty much one more problem, and I think we can do it. All right. This one is all about quadratic forms and features. This is the very first test that we took, okay? This is a quadratic function in standard form. What is the y-intercept of this function? Well, the y-intercept is just the thing that's added or subtracted at the end, kind of like the y-intercept of a linear function, which means the y-intercept is at -24, which means the point is 0, comma, -24. Now you can figure that out by plugging in x equals 0. That would just get rid of this thing and this thing, which all that's left is -24. Okay. Write the function in factored form. Use the factored form to determine the x-intercepts. Dude, remember when this was hard? Remember when we had to teach this for the first time, and now we've done this 80 million times in this class? That's growth, and that's learning. It's 4:41. This is not going to upload in 20 minutes. I'm sorry. I really apologize. You're hearing me almost in live time, all right? And I'm wasting time still. All right, here we go. I'm going to write this in factored form. That means we have to factor it. X squared plus 5x minus 24. 2 numbers that multiply to -24. Add to 5. That's kind of hard, actually. Hold on. Let me think about that. 8 and 3. 8 and -3. Here we go. Multiply to -24. Add to 5. Quick maths. That means this factored form is this. X plus 8 times x minus 3. F of x equals. Then if we need to find the x-intercepts, all we need to do is find the values of x that make the function 0, the output 0, which means we're just finding these things, the values of x that make these 0. That's x equals -8, and that's x equals +3, which means my 2 x-intercepts are at these ordered pairs, -8, comma 0, because that's the output there, and 3, comma 0. Here we go. All right. Last but not least, second thing but not least, is the vertex form of the equation, which actually directly relates to this last problem we just did about transformations, because the vertex form is kind of just telling you the transformations. This number shifts us left and right. This is our horizontal. This one is our vertical. If I'm translating a parabola around, if I'm just moving this around, all I'm doing, if I'm moving it left and right or whatever, is I'm just translating. Oh, stick with it. Come on. I need this, and I need this, and I need to, this is not, okay. Anyway, I'm just going to move the vertex around with it. That's all I'm doing. Okay. So the vertex just happens where you transform it, which means if you can find what you're doing left and right and up and down, you already know the vertex. That means since I'm adding here in the horizontal, my vertex point is going to be -2.5 because I go left 2.5, and then comma -20.25 because I'm going down -20.25, which means my graph is going to look something like this. As long as this point is -2.5 and this point is -20.25, it's just going to be a good old-fashioned parabola like that. And thus concludes the Algebra 2 Semester 1 final review. I got to upload this. Bye.